Hello, this is Dr. Johnson. I am one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson on comparing two populations or groups. We finally arrived at the meat of the course. In this unit, we'll compare two populations or groups by comparing two proportions. So this is, in essence, what we're trying to solve. Suppose that we want to compare the proportion of individuals with a certain characteristic in population 1 and population 2, or we want to compare the effectiveness of treatment 1 and treatment 2 in a randomized experiment. And I give an example at the bottom of the slide. You can read through it. This shows the kind of problems that you can expect to see this unit. First thing we need to do is we need to define the parameters in context. This time we have two populations or two treatments, so we have to define two parameters. So we're going to let row 1 be the true proportion of successful outcomes in population 1 or treatment 1, and row 2 will be the true proportion of successful outcomes in population 2 or treatment 2. Now you're going to have to add context when you are defining your parameters. This is in the most generic sense. Row 1 minus row 2 is the true difference between the proportion of successful outcomes in population 1 and population 2. Now we will need to check the conditions for a two-sample Z interval for the difference in proportions. And I just want to tell you up front that the conditions for a two-sample Z interval are different from the conditions for a two-sample Z test. And it has to do with the last condition there. So the first condition, random. The data has to come from two independent random samples or from two groups in a randomized experiment. So you have an additional requirement this time. You have to say that the samples are independent. We have two independent random samples. And of course, the random condition is crucial for doing inferences. If the data does not come from well-designed random sample or randomized experiment, we can't draw conclusions about a larger population or about cause and effect. So let's talk about the second condition, independent observations or the 10% condition. When sampling without replacement, we need to check that the two populations are at least 10 times as large as the corresponding samples. So in this case, the sample size for the first sample has to be less than or equal to 1/10 of that corresponding population. And the sample size for the second sample has to be less than or equal to 1/10 of the population for that sample. Now, importantly, do not check the 10% condition when talking about experiments. Do not check the 10% condition when talking about experiments or when we're sampling with replacement. Only do the 10% condition when sampling without replacement. Now let's talk about the last condition, and this condition applies only when doing a two-sample Z interval. So in this case, the counts of successes and failures in each sample or group are all at least 10. And we are going to use sample proportion. So we're going to be using p-hats to do this test. So n1 times p-hat1 has to be greater than or equal to 10. n1 times 1 minus p-hat1 has to be equal to or greater than 10, and so on. You have to show that all four of those are at least 10. And as a reminder, we are using sample proportions, p-hat1 and p-hat2. When these conditions are met, the sampling distribution of p-hat1 minus p-hat2 will be approximately normal, with a mean equal to row 1 minus row 2. And this right here is the standard error for a confidence interval, a Z interval for difference in proportions. This is the standard error for the confidence interval. And here I have a diagram showing just what we did here. Now, when the conditions are met an approximate C% confidence interval for the difference between row 1 and row 2 is given by that expression right there. Now, that formula is not on your AP formula sheet, but parts of it are in different locations, so you should be able to just assemble it by looking at the formula sheet. So that's the formula. The Z star comes from a table or from your calculator, and that's it right there. Now let's talk about the two sample Z test for a difference in population proportion. When testing a claim about proportions, row 1 and row 2, there are two ways of expressing the null hypothesis. You could either say that row 1 minus row 2 is equal to 0, or equivalently, you could say that row 1 is equal to row 2. Okay. Then alternatively, you either have the two-tail alternative where you have the not equal sign, or one of the one-tail alternatives where you have a strictly less than or a strictly greater than. Now, as a reminder, hypotheses are always about populations and population proportions. Do not mention sample proportions in the hypotheses. And also I should say this, the hypothesized value, row 1 minus row 2, is often 0, but not always. We can throw you a curveball. The AP exam can throw you a curveball and have you test a situation where they want to know whether the difference between row 1 and row 2 is some value that's not 0. Okay, now here's where the conditions get different. As I said before, the conditions for a two-sample Z test are different from a two-sample Z interval, and it has to do with that last condition, the large count condition. So here is what the condition is for the Z test. In a significant test where we are testing the null hypothesis that row 1 minus row 2 is 0, we need to calculate the combined or pooled proportion to calculate our standard error. So what is the combined proportion or pooled proportion? It is the count of successes in both samples combined, so it's x1 plus x2, divided by the count of individuals in both samples combined. That is sample size 1 plus sample size 2. So we're taking the sum of the number of the successes divided by the sum of the sample sizes. And of course, statistics being what it is, we don't always agree on our notation. Sometimes the symbol for the pooled proportion is to put row with a bar over it. Sometimes you'll see it as the combined proportion as row with a capital C subscript. And then of course, the combined or pooled proportion for 1 minus row is sometimes Q bar, Q with a bar over it. So to check, as I said before, to check that the sampling distribution of p hat 1 minus p hat 2 is approximately normal, this time what we need to do is we need to check that n1 times the pooled proportion is at least 10, and n1 times 1 minus the pooled proportion is at least 10, n2 times the pooled proportion is at least 10, and n2 times 1 minus the pooled proportion is at least 10. All four of those have to be at least 10, and now we are not using p-hats, we have to use the pooled proportion. And why is that? Well, when we're doing hypothesis testing, we get to assume that that row 1 is equal to row 2. So if row 1 is equal to row 2, well then this pooled proportion gives us a more precise estimate of what is the true combined or pooled proportion when we use data. So we get a better estimate by pooling. And so we need to use our pooled proportion when checking our conditions as well. When the conditions are met, the two sample z-test for differences in proportion rho 1 minus rho 2 uses this test statistic right here. So the numerator is p hat 1 minus p hat 2 minus the difference in rho 1 minus rho 2. And if our null hypothesis is that there's no difference, well, then we're going to put a 0 right there. And the standard error, what we have there in the denominator, here is where we have to use our pooled proportion. So what you see there in the denominators of our z-test statistic uses the pooled proportion and P bar and Q bar that I described in our previous slide. So let's go through this problem right here. Our teenagers going deaf. In a study of 3,000 randomly selected teenagers in 1984 to 1994, 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005 to 2006, 19.5% showed some hearing loss. You can see that the proportion is slightly different. The question is, do these data give convincing evidence that the proportion of all teens with hearing loss has increased? So we're looking for convincing evidence. That tells me that we're going to do a z-test, not a proportion. And it's going to be a one-tailed test because we're looking for convincing evidence that the proportion of teens with hearing loss has increased. So we have a one-sided test. So first thing we need to do is define our parameters. I'm going to let rho 1 be the proportion of all teenagers with hearing loss in 2005 to 2006. And rho 2 is the proportion of all teenagers with hearing loss in the earlier period. And we want to see, do the test data give convincing evidence that the proportion of tests has increased? So we're looking for whether rho 1 might be greater than rho 2. So I can state my null and alternative as rho 1 minus rho 2 is equal to 0, and my alternative is rho 1 minus rho 2 is greater than 0. The problem doesn't give us a significance level, so we're going to default to 0.05. So conditions, first thing we want to do, we want to name the procedure. The name of this procedure is a two-sample z-test for the difference between two population proportions, rho 1 minus rho 2. And that can be shortened a little bit. But that one right there, that name there will give you full credit. So we'll perform that test if the conditions are met. The first thing we do, we have to check the random condition. This time, remember, we have to say that the samples are independent. So I say this: the data came from two independent random samples. That meets the requirement I mentioned earlier that you have to say that the two samples are independent. 10%, there are more than 10 times 1,800 teenagers in the period 2005 to 2006, and there's more than 10 times 3,000 or 30,000 teenagers in the earlier period. Now, the large counts condition. I made a table here because I wanted to actually figure out the counts, because remember, we have to calculate the pooled proportion, and for that I need to know the counts. And counts are always going to be an integer. So I take the first sample size for in 2005-2006. I have 1,800 in my sample, and it said that 19.5% show hearing loss. So I take 1,800 times 19.5%, and that gives me 351 with hearing loss, and that gives me 1,449 without. So I get a total of 1,800. And I do the same thing for the earlier period. So now I have the counts of success and counts of failure for both periods. So now I calculate my pooled proportion. You either can abbreviate it with rho with a bar over it, or rho with a lowercase c. And I give the formula there, x1 plus x2 over n1 plus n2. Then I plug in my numbers. I have my counts of successes, the sum of the counts of successes over the sum of the sample sizes, and that gives me a pooled proportion of 0.167. Now, when checking the large count condition, I need to use that pooled proportion. So I take N1 times that pooled proportion and show that that's 301, that's greater than 10. N1 times 1 minus the pooled proportion is 1499. And then I do the same thing for the 1988 to 1994 period. And I see that all of those combinations, the number of successes and the number of failures, are all greater than 10. So we can use our Z distribution. Now let's go to your calculator. This time, when you turn your calculator on, go to Module 2. That's the statistics module. We're going to do a test. So hit F3, F3. What type of test? It's a Z test. All tests of proportion are Z tests. So hit F1. What type of Z test is it? It is a 2-proportion Z test. So hit F4. Now we're going to get calculator input. First thing is, they're asking about, well, what is this? Is this a one-tailed test or a two-tailed test? We are doing a one-tailed test, and the null hypothesis had a, let's go back there, had a greater than sign in our alternative hypothesis. So I have greater than the hypothesized value. Now I put my number of successes, x1, that's 351. I put the number of my sample size for the first sample, 1800. Then I put the number of successes in the second sample, 450. Then I put the sample size for the second, and that's 3000. Okay, I've loaded up all my data. Then I hit execute, and it returns this. It tells me that my Z statistic is huge. It's a very big Z statistic. And the corresponding probability is very, very small. It calculated p hat to be 19.5 and p hat 2 to be 12.6. And it confirms my pooled proportion of 0.167. So I want to write that down on my answer sheet. Okay. Now we want to calculate our Z statistic. On the left-hand side, I gave you the formula for it, and you do not have to write out the formula with symbols, but what you must do is write out the formula with the numbers from the problem in it. So my p hat 1 was 0.195, and my p hat 2 was 0.15. Now, in the bottom part, I have to use my pooled proportion of successes and pooled proportion of failures. I divide it by 1 over the sample size of the first sample and plus 1 over the sample size for the second sample. Now I can run that into my calculator if I have time, and hopefully it will confirm that give us a Z-score of 4.0, just like we got on the previous page. We got a Z of 4.048. So when I ran it through my calculator, I get a very similar score. That's comforting. Now I could go right to the tape. I could go right from my computer results and say that the p-value is 0.00026, or I could confirm that using my normal CDF function. In that case, if I use my normal CDF function, we're trying to find a probability of getting a Z-score greater than 4.0. So my lower bound is 4.05. I guess that's what I got on my previous page. My upper is some arbitrarily large number, like 1,000. Standard deviation is 1, mu is 0. And that tells me that the desired p-value is very close to 0. My calculator said it came to 0.000026. So I say p-value is approximately 0. Now I have to write my interpretation. Since the p-value is less than alpha, and I put in my values for alpha, we reject the null hypothesis. So if we reject the null hypothesis, that means we have convincing evidence that the alternative hypothesis is true, but we have to write it in context. So we say, we have convincing evidence that the proportion of all teens with a hearing loss has increased from 1988 to 1994 to the later period of 2005 to 2006. So between these two studies, Apple introduced the iPad. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? Well, that's a good question. We have a statistically significant increase in hearing loss and the introduction of Apple iPod. Does that mean that we have causation? No. Since we did not do an experiment when we randomly assigned some teens to listen to iPods, and we did not do an experiment where we randomly assigned some teens to listen to iPods and other teens to avoid listening to iPods. Therefore, we cannot conclude that iPods are the cause. So this is just an observational study. It is not an experiment. Therefore, we cannot make an inference about causation. There may be other variables that change during this time period that could cause hearing loss. So that is the end of my presentation. Thank you very much.